This video demonstrates an integrated planning and engineering workflow on the engineer's desktop. This workflow will allow us to get more value from existing data across all applications. The engineer's desktop includes Compass, Casing Seat, Stress Check, Well Plan, and Open Wells, all sitting on the engineer's data model, EDM. We'll be using each of these applications in this demonstration of the integrated planning and engineering workflow. This integrated workflow allows each application to benefit from the other because information is shared across applications. This reduces data entry and minimizes related errors resulting from moving data from ASCII files or manual input. The engineer's desktop provides a collaborative, multi-user environment which allows simultaneous access and updates. Changes in one application can be immediately seen in the other applications. In addition, the EDM data model serves as a single data store for all planning, engineering, and operations data, so there is only one repository to query for all the data. Finally, we can improve our troubleshooting capability by performing detailed engineering analyses using daily report information entered into Open Wells. This allows the supervisor and engineers to collaborate quickly using readily available operations data to prevent downhole-related problems. Each of these benefits will be seen in action as we now step through the workflow. The first step in this integrated planning and engineering workflow process begins with Compass. In Compass, we initially design our trajectory or plan, which is shared across all the applications. The plan is the single most important item since it is indeed shared across all the apps. Within Compass, we will create a new prototype plan. We will tie on from the wellhead and select OK. So now in the plan editor, we can quickly generate a plan to use across all the applications. We'll first create a hold section of 500 feet. And next, we'll use the powerful planning algorithms in Compass. We'll use the optimum align planning method. We'll select a T2 for final target. And we want to project back to our target T1. So now in just a few steps we've generated a new plan. And we can also see the entire planned well path that we've just created. So we'll want to save this plan. We can view this in 3D. We can show our targets. And now we want to add some formation tops. So for demonstration purposes, we'll add formation tops every 1,500 feet. And then we will need to assign a lithology for each of the formations. And we'll just choose sandstone here at the end and select OK. And now these formation tops can be viewed on our 3D plot. So if we select the casing editor, we can see that no casing has yet been defined. So we're starting with a trajectory and no casing specified. So this concludes the first process in the planning phase, which is designing a trajectory. In step 2 of the integrated planning and engineering workflow, Casing Seat will be used to determine the appropriate setting depths and casing sizes for our casing scheme. We will now use the Casing Seat application to define a casing scheme. Plan 1 shows up with the Simultaneous Activity Monitor, or SAM indicator, which looks like a man in blue. This indicator shows there's an active user in Compass on the same machine and the same user, and we have read-write access as indicated by the RW. So now I'll open the plan that was generated in Compass. I'll apply the predefined casing seat template. And we can see here that the lithology table shows the formations that were input into Compass. So this information is automatically populated. And we can choose to insert a row to add to our lithology table. And we'll just call this formation 2A. and assign it a lithology. And we'll enter another one after the third formation. We'll insert a row, and we'll call it 3,500 feet. Formation 3A. Assign a lithology. So now I'll save this plan, and now these new lithologies will be available in all the other applications. So now we'll need to populate the rest of the lithology table. We'll highlight the overbalance margin and differential sticking limit. I'll use Control-C to copy and Control-V to paste in the remaining cells. Now we'll go to the well path editor on the Survey tab, where we can see the well path designed in Compass is automatically populated here in Casing Seat. Notice that the well path is grayed out because it was designed in Compass, and once a trajectory is planned in Compass, it is disabled for edits in all the other applications. Now we'll open the Design Parameters dialog. We can see that the bottom-up design and top-down design have both been selected. We'll choose the first casing OD to be 26 inches at a setting depth of 460 feet, and the last casing OD will be 7 inches. Now in the kick tolerance, we'll just select a kick intensity of 0.5 pounds per gallon. And now what we'd like to do is input the pore pressure and fracture gradient data. And we have this information in an Excel spreadsheet. We'll choose pore pressure from our drop-down list. Go to the Excel spreadsheet. I've highlighted from 400 feet down. We'll copy, and back in Casing Seat, we'll paste the pore pressure data. And this information will be shared across all the applications. Now, generally speaking, Casing Seat is the first point of entry for pore and frac pressure, since this is the first application in the workflow that uses it. So now we'll go to the fracture gradient. Again, we'll go to our Excel spreadsheet, select copy, and in Casing Seat, paste the cells. So now we're ready to calculate all the casing scheme solutions. In the Calculate dialog, we'll just accept all the defaults that are here. We'll go to the Design tab, and here we can see all the solutions that have been generated with the casing hole size scheme available in the template. Now here we're particularly interested in solution 9, in which we have a 26-inch casing, 13 3/8, 9 5/8, and 7-inch. And this will work well for our plan. But again, the user can select any of the possible casing schemes that you would like to use. So again, we'll go with solution 9, and we want to set this as our active well configuration. And now we will save this design. So this is the casing scheme which will be shared across all the applications, including Compass, Casing Seat, Stress Check, and Well Plan. So now we'll go back into Compass and reload the new information which has been entered in Casing Seat. So now in our 3D view, we can look at the formation tops, and we can see the new formations that we added in Casing Seat. We can also view our casing seats, which were defined in Casing Seat, and we can see them defined in the casing editor. So now we can see our plan has Casing Seat as an active user as well in the SAM dialog. So this concludes the second step in the workflow, which is selecting a casing scheme. In Step 3 of the Integrated Planning and Engineering Workflow, Stress Check will be used to design the individual casing strings in our active casing scheme. We have defined casing seat selection and casing sizes in Casing Seat. Now we need to design the individual strings themselves in Stress Check. So hovering over the plan, the Simultaneous Activity Monitor shows that this design is open in both Compass and Casing Seat. So in Stress Check, we'll open the design and select the predefined template and start our casing design. The first thing we'll do is change the 7-inch production casing to a liner. And then we'll also change a 9 5/8" casing to a production casing. Then we'll want to change the top of the cement for the 7-inch liner to about 500 feet above the 9 5/8" shoe. And we'll specify the hanger for the liner to be the same. So we'll start by designing the 7-inch production liner. So to review, we can see that we have our pour pressure already defined, our fracture gradient, and our well path. And all this information has been populated directly from Compass. So next we'll define our production data. We use a fluid density of 10 pounds per gallon, and we'll specify a packer depth of 13,000 feet. Now we'll look at our design parameters. And here we have the option to define the design factors, but we will use the default values in this design. And you can see that the design factors can be entered for both the pipe body and connections. So next we'll define our burst loads for the 7-inch liner. We've selected a pressure test for our drilling load, and for production loads we have tubing leak and injection down casing. We'll go to the Edit tab to give the details of each of these loads. For the pressure test, we'll use a pressure of 6,500 psi, and we'll use the default mud weight. For tubing leak, the defaults are given, and for injection down casing, we'll specify 4,500 psi. Now we'll define the collapse loads. We have a drilling load that is cementing, and the production loads are full evacuation and above and below packer. Again, we'll go into the Edit tab for the details, and the cementing defaults are given, and same with full evacuation. And for above below packer, we'll specify a density below the packer of 2 pounds per gallon. And finally, we'll define our axial loads for the 7-inch liner. We'll use a running speed of 3 feet per second, an overpull force of 100,000 pounds, a green cement pressure test of 2,500 psi, and we'll have the service loads selected. So now that the load conditions are set, there are 2 ways to design the string. The first method is to design the string manually, and the second method is to allow Stress Check to automatically calculate using the minimum cost algorithm. So we'll select the minimum cost solution for this case. We'll use the defaults of a maximum of 2 sections and a minimum section length of 1,000 feet. In the Design tab, we want to choose design regions within the triaxial design ellipse. We'll select the upper right region of additional burst capacity under increased tension, and the lower left region of increased compression rating under collapse pressure conditions. We'll then unselect the region outside the triaxial ellipse where combined burst and compression loading can cause failure. So now that the design regions have been defined, we'll choose the minimum cost function. And this will go through the pipe inventory and determine the lowest cost casing scheme solution. So the solution casing scheme here will cost almost $78,000 for this scenario. So now that StressCheck has found the solution, we can go through the tabs to view the solution results. So in the Solution tab, we can see that StressCheck has chosen for the 7-inch pipe a weight of 29 pounds per feet and a grade of N80. In the Design tab, we can see the burst, collapse, axial, and triaxial design loads and pipe ratings for the 7-inch production liner. If we go to the Safety Factors table, we'll be given the minimum safety factor for the 7-inch production liner at each depth for each loading type. And there are codes to show which load case is driving the design at a particular depth. For example, the pipe burst is driven by the pressure test load case over the entire length of the string. Now we can look at the design limits plot, where we can see where the load conditions are represented relative to the API and triaxial von Mises criteria. In this case, the design is within the criteria limits. And now we can add some connections in the Connections dialog. We'll use the API standard LTC connection for the 7-inch production liner. And StressCheck automatically shows the safety factors for the connection that we've selected. So now we'll go back to the Safety Factors table to verify that our safety factors are acceptable. And we can see how our connection information compares with the safety factors for the pipe body. So we can see for the axial load, the connection is driving the design through connection jump out. So now we'll design the second string, the 9 5/8" production casing. So we'll go back to our Work tab. We'll select the 9 5/8" production casing. And we'll quickly go over the criteria to do this design. We'll first select the burst loads. For drilling loads, we have gas kick profile and pressure test. For production loads, there's tubing leak and injection down casing. For our gas kick profile, we'll select a gas kick of 25 barrels and an intensity of 0.1 pounds per gallon, and a drill pipe of 3.5 inch, a 5-inch OD collar, and a collar length of 450 feet. For the pressure test, we'll use 6,500 psi test pressure consistent with the pressure we used for the 7-inch liner, and then we'll use the default value for the mud weight. For tubing leak, we have the defaults already there, and injection down casing, we'll use 4,500 psi, again similar to the 7-inch liner specification. So next we'll define the collapse loads. We have cementing drilling load and full evacuation and above and below packer production loads. The cementing defaults are set. No more information needed for full evacuation. And then for above and below packer, the density below the packer will be 2 pounds per gallon. And then we'll let the software automatically calculate the pore pressure at the perforation depth. And finally, we'll select the axial loads. We'll choose 3 feet per second running speed, an overpull of 100,000 pounds, green cement pressure test 2,500 psi, and again we have the service loads checked. So we'll use the same procedure as before to design the casing string. Recall that the two design methods are manual or graphical, and then computer generated using the minimum cost algorithm. So we will use the minimum cost algorithm. Again, we'll use the defaults for maximum number of sections and minimum section length. And in the design case, we'll again choose the same as for the 7-inch liner. Okay. And then we'll select our minimum cost design. So the computer is filtering through different iterations to find the best solution from the catalog. And we'll see that StressCheck will find a solution that is best for this case, and it costs almost $200,000 here. So next we'll go to the Solution tab to see that StressCheck has chosen a 9 5/8 inch pipe with 53.5 pounds per feet and grade N80. So for this demonstration, we'd like to choose two 9 5/8 inch string sections for the solution. So we'll need to go to the Design tab and view the design plots. So to select two strings, I'll double click next to the pipe rating line. I'll grab the design line and move it over. So now we can see there are two different sections in the design. So now if we go back to the Solution tab, we can see the two sections are displayed. The upper section has 53.5 pound per foot N80 pipe, and the lower section has 58.4 pound per foot C90 pipe. And the total cost is also displayed. Now we'll look at the safety factors to make sure we meet our design factor criteria. Everything looks acceptable for this string. You can see at the bottom, StressCheck indicates whether the axial load is in tension or compression as indicated by the parentheses. We can now look at the von Mises criteria to see if the design is okay here. And here the loads are all well within the design limits boundary. We can right-click and select Properties to look at the other section as well and make sure this design is within the criteria. As a final step, we'll specify the connections for these two casing string sections. We'll choose API buttress connections for both cases. And the safety factors are automatically shown, and the cost is given for these connections. At this point, we have completed the design for the 7-inch and 9 5/8 inch casings. For demonstration purposes, we'll stop our design here, although we could continue by designing the 13 3/8 inch and 26 inch casing strings. Now we will save the casing design to complete the third step in this workflow. The design information for the pipe and connections will be saved into the database to be available in WellPlan for further operational analysis while drilling. In Step 4 of the Integrated Planning and Engineering workflow, WellPlan will be used to perform a torque drag analysis for our current design. In WellPlan, we can capitalize on the StressCheck design. We see we have three applications open with this design: Compass, Casing Seat, and StressCheck. At this design level, we have the well path, pore pressure, fracture gradient, and geothermal gradient all carried over. So within WellPlan, we'll create a new case under this design. And we'll open this new case. And in WellPlan, we'll do a quick drag chart and model the 7-inch liner designed in StressCheck. In this case, we can see that we have our well path automatically carried over. In addition, we have pore pressure and fracture gradient. But at this point, there's nothing in the whole section editor or the string editor. So what we want to do is copy a string from StressCheck and have this populate the string editor. We'll choose a 7-inch production liner. And notice that the only strings available here are the ones that we designed in StressCheck because these are the only ones with detailed dimensional information which is needed in WellPlan. So we'll select OK, and then a dialog asks us if we want to copy a string to the whole section editor, and we'll choose the 9 5/8 inch casing because that's what we're running the 7-inch liner in. So now we can see the 7-inch 29 pound per foot N80 pipe that we specified from Stress Check. But now we're lacking what we need to run the liner on, so we need to add a drill pipe section. We'll choose a 3.5 inch and select OK. So now we want to go to the whole section editor. And here we can see that we have the two 9 5/8 inch casing sections automatically populated in the editor. You can see the N80 and C90 pipes that we designed in Stress Check. And we also have the open hole section listed below the casing. So one thing that's lacking here is the friction factors. Stress Check does not use friction factors, so we need to input them here. And we'll go ahead and use 0.25 for the cased hole sections and 0.35 for the open hole section. And finally, we need to define our fluid. Go to the fluid editor and select the first fluid here and activate and hit OK. So now we'll go into the torque drag module and we'll select the drag chart mode and we'll select our run parameters. We'll look from 8,000 to 15,000 feet with a step size of 100 feet. And we'll just look at tripping in and tripping out. We'll select OK. Now in our torque drag setup, we'll give a traveling assembly weight of 25 kips and select OK. So now we can quickly look at a tension point chart. We can see that the tripping in and tripping out curves are well within the confines of the yield and the buckling. So we've shown we can quickly come into WellPlan, use all the information previously entered from other applications to populate both the design and the case, and with minimal input we could quickly look at running this liner and evaluate a drag chart. This takes us to the last phase of this integrated planning and engineering workflow. In the last phase, we'll use OpenWells and WellPlan together. We'll use WellPlan to analyze actual report information entered into the daily report in OpenWells. So now we can use a new feature in WellPlan to create a new design and case from OpenWells. We'll assume we've started drilling, and this well has some daily report information. We'll choose Daily Operations Report 26. And if we're interested in a particular time, we can scroll through the snapshot time to select our time of interest. Because we could have multiple BHAs and mud checks, so the time we select here will determine what gets populated in WellPlan. So now as we select Finish, it goes to the OpenWells Daily Report to populate the new WellPlan case with all the information. And we'll go ahead and apply a predefined workspace which sets up a series of tabs for our workflow. We'll right click and choose Apply. So now we can have the current surveys at this point populating the design. In addition, in the whole string editor tab, we can see the whole section populated from OpenWells, and we have the detailed BHA information all taken from the daily report. So all the information we need is populated from the OpenWells daily report. Now in this case, the supervisor complained about hole problems. So we'll go into the torque drag module and once again look at the drag chart. We'll define our run parameters from 8,000 feet to 10,000 feet, stepping every 100 feet. We'll rotate on bottom with a weight on bit of 10,000 pounds and a torque estimated at 3,500 foot-pounds. And in the torque drag setup, we'll just go ahead and keep these defaults that we have here. And next we'll go into the tension point chart. And what we see here are the predicted loads, solid lines, which are based on the friction factors in this whole section editor. And also we can see the actual data indicated by these markers as brought in from OpenWells. Now if the actual loads deviated from the planned loads by a consistent amount with depth, then we'd estimate that the friction factors were off a bit. But the actual data is slowly increasing away from plan, which indicates that there's some problems going on here. If we look at the torque chart, we also see that the torques are increasing relative to the plan that we anticipate. So if we go back to the survey, we can see we have a relatively long horizontal section, so hole cleaning could be a problem. So this is the next thing that we'll want to investigate. So we'll go into the hydraulics module and choose a hole cleaning mode. And the transport analysis data will have a rate of penetration at 200 feet per hour. And we'll assume 0 rotary speed, which would simulate a sliding scenario. And we're circulating at 600 GPM. We'll say a cuttings diameter of 0.125. And we're drilling through shale, which gives us a specific gravity of 2.65 and a porosity of 15%. And we'll calculate every 100 feet. So if we look at our minimum flow rate plot, we can see that at 200 feet per hour penetration, we're barely cleaning the cased hole section. But we're well outside the bounds of what we need to clean the open hole section. So in fact, we could be having hole cleaning problems. So we could either increase our circulation rate to roughly 750 GPM, or we could reduce our RPM. So for rotating, this will improve our performance a little bit. So let's say 60 RPM. And we can see that this helps some, but what we'll want to do is we want to look at our worst case scenario, which would be sliding, so we're going to leave it at 0 RPM. So let's assume we want to increase our circulation rate. We first need to make sure we don't exceed our system pressure. So to do that, we need to look at the pump rate range plot. So we'll choose mode to be pump rate range. We'll look at our circulating system. We can see that our rated working pressure is 5,000 psi, and we have several mud pumps that have been copied in from OpenWells. Go to parameter rates. Our minimum pump rate is 600 GPM. Our increment will be 50, and the maximum pump rate is 800 GPM. We'll assume the maximum pump pressure is 4,500 psi, and we'll give it 1,800 horsepower. And we'll select to include the tool joint pressure losses, mud temperature effects, and we'll use a string editor bit nozzles. So next we'll go to the pump rate pressure plot, and we can see that even at 750 GPM, we're still way below the system pressure. So we can safely assume from a mechanical standpoint that we can increase our circulation rate. So the last thing we need to do is make sure we don't fracture at the shoe when we increase our circulation rate. We'll need pour and frac pressure information, which was not populated from OpenWells. But in WellPlan, we have a well planning report, which is this long horizontal stretch design. And this design has pore and frac pressure information there, and we can capitalize on this data by dragging it and dropping it into our existing design. So we'll go ahead and do that. Select yes. And again, for our frac gradient, we'll copy that into our design. Select OK. So once this is defined, we can come into the ECD versus depth plot in pump rate fixed mode. We'll want to select our rate parameters, and we'll give it a pump rate of 750 GPM and hit OK. And then what we'll do is look at the ECD versus depth plot, and we can see here that the annulus pressure is well below the fracture pressure. So we can safely assume from a reservoir standpoint that we can increase the circulation rate to 750 GPM. So our recommendation is to increase the circulation rate to see if that alleviates some of the tight hole we're having. So we've seen the ability to quickly populate a well-planned case with actual open wells data, perform a quick engineering analysis to look at some trouble areas we've been having, and we're able to make a recommendation based on using the data across two well-planned modules, torque, drag, and hydraulics. So this concludes the entire integrated workflow from start to finish for integrated planning and engineering. In summary, you've seen how we've started by designing a trajectory in Compass and sharing that trajectory information with Casing Seat. We entered pore pressure and fracture gradient information in Casing Seat, determined the Casing Seat locations, and then moved into Stress Check for a detailed casing and liner design. We capitalized on that design and well plan for the planning phase. We quickly looked at a drag chart using all the information that was previously populated in the other applications. We also used WellPlan to take actual data from open wells to make use of it, analyze the situation, and come back with some recommendations. This demonstration showed the benefits of this integrated planning and engineering workflow, including the collaborative multi-user environment, reduced data input, and the utilization of actual data from open wells. Thank you.